So students, I think all of you have understood the concepts uh, based on the Mealy state machine, right? Do you still have any doubts as to how to implement this sequence detector? Are the concepts clear?
Yes, sir.
Yeah, okay, fine. So in that case, then we can move on to the next concept. So I hope Mealy state machine is understood, and in the same way, once you have Mealy state machine, okay, you can always get back, or you can draw the other type of state machine, which is nothing but your Murray. Okay, so the only representation here is, in your Mealy, you will have input by output, and the state will be represented as S naught. Okay, and in your Murray, okay, it will be S naught by output. Okay, and input is actually given to the state. Okay, so this is the main differentiation. So in Mealy, the output depends on present state and present input. So input and output, it is dependent. But in Murray, it depends on present state only, which is the input. Okay. So now if you can see the diagram, you can easily understand what is this present state. Okay. And M is nothing but your memory, your input, then how it is connected, your present input, what is your present input, what is your present state. Okay, so connecting back the output of memory to your input becomes your present state. Okay, and your present input is nothing but those general inputs that you give. Okay, those becomes your present inputs. Outputs of memory becomes present state. Okay, so those you give to your inputs. So part of your memory also comes in, and the normal input is also given to your output. So this is one of the representation of your Mealy state machine. More than this diagram, okay, you will be very much clear with the initial first diagram which I showed you all, right? Yeah. So now that you know your sequence detectors, okay, now that you know how these things are functional, right? So now it becomes very easy for you to analyze this diagram. You have input, then logic, excitation, memory, your state variables, and your output logic. So ultimately you have your input, you have your memory, and your output. Okay, that's because these are not combinational circuits, these are sequential circuits. And we call it Mealy because the output is dependent on what? Your memory as well as your input. Okay, so input by output, so this is nothing but your input by output. Okay, so this becomes your input, and this becomes the output of memory. So input by output. uh, Here, okay, the it is only dependent on the output. Okay, it's not dependent on the input, so the input doesn't come inside the state diagram. Okay, it comes outside. Okay, so I hope this is very much clear for all of you. Any doubts here, students?
No, sir.
Can I proceed? Okay, fine. So today we will look into a different concept called design of counters. Okay, so it will be asked in your examinations for sure. It could be your internals, or it could be your semester end examinations. Okay, so what all concepts we have discussed so far, so these will be implemented for design of counters. Okay. Can someone tell me what is a counter? Why do we use a counter? Where are counters employed?
It's a register, sir.
Okay. And then
Examples would be from clocks to stopwatches and stuff.
okay.
Sir, with counters, we can not only count, but we can also measure frequency and time.
Frequency and time. How is it? Can you please explain? Yes, that is a good answer. Please, can you explain?
Sir, counter is equal to the count held in the circuit by the flip-flops, and
Hmm.
counter is they are specially designed synchronous sequential circuits.
Okay.
So, uh, like in increment memory address, we can measure frequency and time.
Okay. Fine. So for thank you for those answers. Now for anything, okay, for any circuit to function, okay, we need a very important component called a clock. So without clock, things wouldn't synchronize. Okay. So when I say synchronize, at a particular instant of time, something has to happen. So if that doesn't happen, then we can say that things are not happening on time. Okay. So that's the meaning of a clock. Now, as you all know, okay, we use clock in our day-to-day lives. Okay. So it can be with regards to the traffic lights. Okay, even there we have these clock pulses. We have counters there, right? And we use it as your friends mentioned. Okay, we use it in stopwatches. Okay, we use it in wristwatches. So clocks play a very important role. Now, with regards to digital circuitry, at a particular instant of time, we have to make sure that an event occurs. Okay, so if the event occurs exactly at that moment, then we can say that you know uh, that the purpose is served. Okay, right. So here we'll be studying about synchronous sequential machine. Okay, so these synchronous sequential machines are also called as counters. Okay, keep in mind the synchronous sequential machine is also referred to as counters. Okay, now synchronous happens only with clock. Okay, only if there is a clock. Okay, right. Then what's the sequence? Sequence means what?
Ordered set of bits or
Ah,
instruction.
yes, it has a some kind of order. Okay, it has a sequence. Just like how we studied about the bit pattern. Okay, I told you about 1010. Okay, so I can say this set as a sequence. If this is changed, okay, if I say let's say I have two zeros and two ones, even if I reorder them, okay, here also it is two zeros and two ones, but I cannot say that this is a sequence, right? So the sequence actually matters one after the other. So exactly one after the other, I need to have those particular bits. So I can say that this sequence is good, which means detected, and this sequence is incorrect sequence, even though it has the same number of ones and zeros. Okay, Fine. So synchronous happens with respect to clock. Okay, so clock is involved in getting a particular a train of pulses executed. Okay, and something which has both of them, the clock and sequence. Okay, which executes this. Okay, we term it as a machine. Okay, most counters do not have any inputs but go through a fixed sequence of states on successive clock pulses. Okay. Now you would have seen your binary numbers. Okay, starting from 00. Okay, from 00 to the highest value 1. I'm just taking 2-bit example here. So here, if you can see, it's a gradual increment of numbers from one binary value to another binary value, right? So which means there is a sequence that is happening. There is a sequence. So this sequence of states, now you all know what is a state, right? So state is something in which the circuit is present, and there are few set of inputs and outputs, and if the input is favorable, okay, then it will move on to another state. So if it's moving to another state, and if it's a planned state, then it becomes a sequence. Now all this is controlled with the help of something called clock pulses. Now I think you have exclusively studied about the edge triggered and level triggered, right? So we have something called positive edge triggered, and we have something called negative edge triggered, right? So some circuits will be calibrated to work for positive edge triggered, and some will be calibrated to work for negative edge triggered. Okay, so based on what kind of calibration is done, okay, we can find that these clock pulses, okay, will be activated, and the circuit responds to those rising value or falling value. So I hope all these concepts are clear by now for all of you, right? So now we have an example. Okay, I've taken one complex example. If you can solve this, okay, then any other example can be solved. Okay, so we will just look into this, and we will see how these counters can be designed. So the question says design a synchronous 8-bit. Okay, so they are giving us a clue that it is 8-bit, so which means I have to start from 000, right? I will have 3-bit synchronous 8-bit binary counter using JK flip-flops to count the number of instances that the input coincides with the clock when the clock is high. So whenever the clock goes high, okay, we want it to move to the next state. That is the meaning of the question. Have you all understood what is the meaning of the question? Yes, have you all understood what the question is trying to tell us?
Yes, sir.
Okay, fine. So they have specifically told us to use JK flip-flops. Okay, sometimes uh, I may even ask you to use T flip-flop or D flip-flop for its implementation. Okay, so you should be knowing your truth table, you should be knowing your excitation table, you should be knowing the conversion table. Okay, so all these are required, just like how we had worked out previously. Okay. Now the catch is whenever the clock is high, okay, whenever the clock goes high, it should count the number of instances. Okay, so which means it should start from 0 and check as to how many clock cycles are high. Okay, so how do we get started? Uh, a 3-bit binary counter will have 2 raised to 3 or 8 states. Okay, so we are very much aware of that. So we start off with 0, 0, 0. Okay, so we go to 1, 2, 3, 4, 5, 6, 7. So do we have 8 states now? Yes, we do have 8 states. Next, let x be the input which is to be counted whenever its value is 1 at the instances of clock. So we will give x as the input. Okay. So what we'll do here is, so I will take x as input and I will check as to whenever the clock goes high. Okay, I will make sure that it is changing. Okay, the state diagram of the system is as shown below. So as I told you, I will be using these clocks, okay, starting from 0 to 111. Okay, so we will be having about 8 states. Now see the beauty of this uh, diagram, the state diagram. Okay, it is going to the next state only if the value is what? Only if the value is high. Okay, if the value is low, then what is happening? It is staying in the same state. It is not moving forward, right? So you can see that we have designed the state diagram, okay, wherein it goes to the next state. It keeps counting whenever we have a high value. Any doubts here, students?
No.
Okay. So the question here will be only, you know, just a minute. Yeah. So the question here will be only till here. Okay. This is only till here is going to be your question. All this you have to design. Okay, you have to design the state diagram, you have to analyze it, and you have to explain as to what is actually given in the example, all those things, right? So so in the state diagram you can see that it is moving to the next state only if I have a 1. I hope till here we have no doubts. Is it? Can I proceed now?
Yes, sir.
Okay, good. So if you can understand the problem very properly, okay, so you can actually design this state diagram in your mind itself and directly start drawing it. Okay, see, as soon as we saw the question 8-bit, and then it starts counting, and then we saw that we need to have 8 combinations, right? So immediately we get to know, okay, fine, it's 2 raised to 3, and then I start from 000 to 111. I'll get 8 combinations. If it's 1, I'm going to the next state. If it's 0, it will stay in the same state, right? Okay, so now whatever I have here in state, I will be putting it in the form of my tabulation. Okay, so what I will do here is I'll be using a b c x. Okay, so x will be actually counting the number of high, okay, that happens. And can you tell me what is this a plus, b plus, and c plus?
So the next state.
Yes, the next state. Okay, fine. So yeah, so a, b, c are going to be your inputs. Okay, so these are your present state inputs. So we will have to draw a line so that you don't get confused.
Sir, one doubt here.
Yeah, tell me.
Sir, do the counter have limits? For example, if like clock, it doesn't have any limit. So if we are counting, for example, about 100 people, and it suddenly goes to 1,000 people, so can the counter count it?
It can count. It can keep going. provided
Okay.
you give the limit. See, for example, I think you would have studied in your lab experiments about this 7-segment display,
Yes, sir. Yes, a
right?
7-segment wheel.
Huh. So in 7-segment display, if you just have one digit, okay, if you just have one pin, one IC, it will show you only one digit, isn't it? So the maximum that it can go is from 0 to 9. Can I show 10 on that single component?
No.
No. So for that, what I have to do, I have to use one more 7-segment, right? So if I
Hmm.
use one more
Hmm.
7-segment, what will happen? It can start from 0 0, right? And it can show me values up to what? 90.
Yes, sir.
Similarly, if I add one more, then it can go up to 1000 values. Yes or no?
Hmm.
So
Yes, sir. Yes.
ultimately, what is happening as you keep increasing its capacity, it can actually show.
So, sir, if we are increasing, so we are adding up to their powers.
Yes, we are adding.
Okay.
Okay.
Yes, sir.
Yeah. So what we are trying to do here is we are trying to understand as to in this example, okay, what we are doing is we are just taking it to be from 0 0 0, okay, to 1 1 1. So 0. So if my input is 0, okay, if the clock is 0, so what you can do is you can just imagine this x as you can just put it as 0 1 0 1 0 1 everywhere, 0 1. Okay, so when it is 0, my inputs will be the same. Okay, so now think of this here. My input is 0, okay, and if the clock is 0, okay, if the clock is 0, then what is going to happen? It is not going to change, but it is going to be in the same state, 0. Understood? So basically, I am writing this in such a way that I am checking for this value. Now let us go to the next state. Let me see if I can get a proper, yeah. Fine. So now you check. Okay, you have this here. Now when my clock goes high, okay, so I am checking for clock going high. When my clock goes high, then what am I doing? I am moving from 0 to what? 1. Is it 1? Are you all understanding what I'm trying to say? Yes, no.
Yes, sir.
Okay. So what is happening here is we have possibilities of 0 and 1 for every state. Okay. So we just have 8 from 0 to 111. Okay. But here I'll be checking for cases of 0 and 1. So which means just imagine 0, 1, 2, 3, and so on. Okay, till my highest value 111. So when it's in 0 state, I have to check if the input is 0 or if the input is 1. Correct. So if the input is 1, it will go to the next state. Okay, next state, NS. It will go to the next state. If it is 0, then it will be in the same state, which is present state. So which means for every value, I have to keep checking for 0 and 1. For every value, I have to keep checking for 0 and 1. Understanding? Right. So here, see, these both are 0. Okay, 000, 000. So I've checked for 0. See, now I'm going to check for 1. 001 is 1. 001 is 1. Okay. So 1, when my clock is 0. When my clock is 0, it will stay in the same state, which is 1. Right. So 1 will remain 1. So 1 will move to 2 only if my clock is high. Understanding, students? Are you able to understand? Any
Sir,
doubts?
can you
Please
explain cell number 3 once again?
ask. Cell number 3. Okay, tell me what is your doubt here, Sahil.
Sir, from cell number 2 to cell number 3, like B plus value, how is it becoming 1, sir?
How is it from cell number?
From 2 to 3.
From 2 to 3. Okay, I am putting it 0 and 1. That's what I told. No, I am checking for 0 and 1. These are from me. This X value is from me. Understood? This value is from me. I am giving 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1. Why am I doing that? Because the clock goes high and low, right? See, the clock will be low, high, low, high, low, high. So when it's in this state, 0. When it is here, 1. Then 0, 1, 0, 1. So this is nothing but your X. Understanding?
Yes, sir, got it.
Huh? Okay, so you can even start from 1, no problem. 1 0 1 0, anything. But normally we tend to start from the low value 0. Okay, so each value is checked. As I told you here, each value is checked for its possibility of 0 and 1. Any doubts? Any doubts up till here?
No, sir.
Okay, students, others, have you understood? Girls? Nikita?
Yes, sir.
Okay, fine. Lavanya?
Yes, sir.
Fine. Okay.
Yes, sir.
So any doubts, please ask. Okay, because it is going to be difficult if you don't understand. Right. So now let's move to the next state. Okay. So in the next state, what is happening? Now I am in what state? 1. Okay. So see, parallelly you have to think. Okay. So here you are going from 0. Okay. So let me just put it here. It will be easy for you. Yeah. See these two. These two is what? 0. Okay. Then these two are this 2 is for 1. Okay, I'm talking of only this column. Concentrate on this column only. Okay, and within the blue line, and then now 0 1 2. So the next division that we have is here. Then the next division we have is here. Are you all able to understand the divisions in the truth table?
Yes, sir.
Yeah. 4, this 5, and then this is 6. And this one is 7. So I have drawn divisions now. Okay, I have made it subcategory. Okay, and now if you can see, let me write it. Okay, so what is this 4 and 5? Cell number 4 and 5, we are checking for what? 4 and 5 we are checking in cell number 4 and 5, we are checking for what value?
0.
No.
2.
This one, yes.
Sorry,
I'm
2.
only talking of this, yeah, 2. Okay, and this one is your 3. And that's what I told, concentrate only on this column within the blue line. From here to here, you concentrate, that's all. Then this thing here is what? 4. Okay, and this is going to be your, going to check for 5. And here, what value is it? What value is it?
6.
Good. And at the last?
So 7.
7. Good. So now I hope you have understood this part, right? ABC part, isn't it? Have you all understood ABC part? How we have got this ABC? Yes or no? And this is going to be your clock. Okay, as I mentioned, your clock values. Okay, it will be moving from 0 to 1, 0, 1, 0, 1, everywhere 0, 1, because it's low, high, low, high. Okay, so the this is like a clock. Okay, fine. So based on this, we will be going to our next state, which is A plus, B plus, and C plus, right? So I hope now you have an idea as to how, you know, we are looking into ABC and how this X is playing an important role, right? And how we are migrating from the present state to the next state. Okay, so that is what it says here. Let X be the input, which is to be counted whenever its value is 1 at the instances of clock. Okay, so we have made sure that it is 3-bit. Okay, and we have made sure that it's a counter, and we have made sure that there are 8 states from 0 to 111. Okay, and we have also included X in our tabular column, right? And the other thing is, it should be counted whenever the value of X is 1. Okay, so whenever the value of X is high, okay, then only it should count. So this X is what I am considering here, okay, as 1. So this is moving from one state to another state. Okay, so which means I'm moving from 0 to 1. Okay, only if my value is high. What value is this? This is corresponding to the clock. Okay, so only if the clock goes high, only if it's high, sorry, only if it's high, then only you will be moving to the next state. Okay, so we can take this as low and we can take this as high. So whenever it is high value, okay, it will move to the next state. So this 000, okay, 000 till 111, okay, is going to be our normal count that we do. Okay, the normal count that we do. To that we are adding X. Okay, to that we are adding X. So this becomes my A, B, and C. Okay, and X becomes my what? Clock. And I will just make sure that how they are moving from one value to another. So I hope students, you are able to understand as to whatever concepts that I have discussed so far, isn't it? Any doubts, please ask, because I do not want to move forward having doubts.
No doubt, sir.
Okay, fine. So now we will get back to our tabular column, okay, and understand as to how we have got this. So I'm just making sure that it will be easy for you to understand. So now I think you are able to understand as to where I'm putting these separations, isn't it? Okay, so now that we have our separators, okay, so it's going to be easy for us to understand. Right, so here also I'm going to check for 0 and 1 value for the values of 0, for the values of 0, right? So yeah, so when my inputs are 0, okay, when my inputs are 0 and the clock is also low, it will stay back in the same state. It will stay back in the same state, which is 0. So this part understood. Now let us go to the next state. It is going to a higher value. Okay, it is going to a high value. Clock is moving from 0 to 1. Okay, so we are in a high state now. So when the clock is moving from 0 to 1, if it is 0, okay, then it will move to the next value, which is 1. Okay, right. So now we will check for state 1. When it is 1, okay, and the input is 0, which means the clock is 0, then it will stay back in the same state. So this one will stay back in the same state. 1 remains 1 itself. Any doubts here, students? Please respond. Any doubts here?
No, sir.
For every case, you have to check for both zeros and ones, okay, because that's what we are doing. So if it's 1, then only it's going on to the next one. If it's 0, then it will stay in the same state, just like how you have seen in your state diagram. Okay. So similarly here, if you can see the fourth cell, okay, if you can see the fourth cell, then since the value is 0, so the same state is continued. It's 1. So what is going to happen? 2 is going to become 3. Okay, here it is 2 and it's going to become 3 here, just because of this value, just because of this value. So wherever there is 1, you can see that it is incrementing. Okay, so it's 3 here in the 7th cell, and here it's becoming 4 because the clock is high, right? So similarly, now look at the last state. Okay, look at the last state when it is 111. Okay, and the value is high. Okay, and the value is high. So what is going to happen is it will not go back to another state, which means an incremental state, but we will restrict it to the initial state, which is 0. Nirmit, you were asking me one question, right? Sir, how will it go to the next level? Isn't it? Are you there in the meeting? Nirmit Verma?
Yes, sir.
Yeah. So this is where we make those changes. Okay. So here I am telling my circuit after 111, you go to 0. Okay. So instead of making this, instead of doing that, if I tell my circuit to go to 1, 0, 0, 0, then the count will continue. Understood? Okay. So this 15th,
Yes, sir.
this 15th cell is actually valuing what? It is valuing 7. 7 is the equivalent, right? So if I tell when the clock goes high, you go to 8, okay, this value 8, okay, then that will happen. So this is where we make changes in our circuit. This is where we make changes in our tabulation column. So I hope all of you have understood as to what is the difference between A and A plus, B and B plus, C and C plus. Understood, right? Can I move on to the next tabulation? Okay, fine. So building the complexity of this one, since in your question, we have asked or we are discussing about JK flip-flop, so you will have to know the excitation table of JK flip-flop. Now, can someone tell me how do we get the excitation table? Can you recollect? Recollect and tell me what is an excitation table?
So from the characteristic table.
Okay, what is a characteristic table? How do I get characteristic table? Based on my?
So that will come from the truth table, no, sir? Like once we start grouping.
Yes. So we get from the truth table. So ultimately, first you should know the truth table. Next, you should know the characteristic table. After characteristic table, it's going to be your excitation table. So there are 3 types. Okay. So I have directly written the excitation table of JK flip-flop. Okay. So this is my present state Q, and this is my next state Q plus. And for what inputs this is going to be excited. Okay. Right. Now, if we can go back a little, okay, and if we can see those block diagrams, there you actually have your excitation state. E. Do you all recall? There's something called circuit excitation. See, circuit excitation. Yes. Are you all seeing this? Okay. So this is nothing but your excitation table. So what I give and how my memory is reacting, and after the memory reacts, what output I'm getting and how it is actually impacting my output logic. So how am I getting my output logic? So this is what we are talking about, the excitation and how we are exciting the memory. Okay. Now, are you able to relate between the block diagram, the state diagram, the counter design? Are you all able to relate as to what we are trying to do? Yes. Okay. Right. So we have this excitation table. Okay. And this can be used to obtain the excitation table for the example, which is nothing but your circuit excitation table. So what I will do here is I will just have my tabulation, okay, which is having my state transition table. So when I say state transition table, it will have my present states and my next state. So I will be getting this table from my state diagram. So state diagram, I'm extracting the value and putting it in tabulation form, so that becomes my state transition table. Next, I'm going to create something called circuit excitation table. Okay. So this is my circuit excitation table. So here, till this, you have already seen. Yeah. So till this section, you have already seen. Yes or no? This is your ABC, and this is your A plus B plus C plus. So till here, you all have seen. Now the one that we are going to create is only from here to here, okay, which is JA, KA, JB, KB, JC. Now, can someone tell me how are we getting these values? If you can recall the previous examples. Yeah. Can you tell me how we are getting this? Now you can look at your circuit excitation. Okay. Now I want all of you to pay attention here. Okay. Right. Compare A with A plus. Okay. So this A and A plus is going to be your Q and Q plus. Okay. So for A, here I have 0. Okay. And here also I have 0. So what is my combination for 0, 0? For 0, 0, what is my combination? 0 don't care, isn't it? So we are looking at this state now. So for 0, 0, 0 don't care. So that 0 don't care is what you are getting here. For this don't care, I have written a dash. Understood how we are getting JAKA? Students, are you all following?
Yes, sir.
Okay. So what I will do is I will compare A plus B plus, then B plus, and then C plus. C plus, and I'm going to get my JA, KA, JB, KB, and JC, KC. Okay, so you have to be very careful here when you're doing this tabulation, because by mistake, okay, if you compare different values, okay, then what is going to happen? You might make mistakes here. So if this goes wrong, then everything is wrong. Okay. So once we have the values of JA, KA, JB, KB, JC, KC, what I will do is only those, okay, only those values I will put it in my K map. So for JA, I will have a separate K map. For KA, I will have a separate K map. JB, KB, JC, KC. So how many equations will I have now? How many equations will I get?
Sir, 6.
6 equations, right? So 6 K maps and 6 customized equations. So accordingly, once I get those equations, I will be working out with the diagram. Now, what I want you all to do is just complete this table. Okay, complete this table and come out with equations for JA, K, JB, KB, JC, KC. Come out with equations for this, and we will continue our discussion as to how this can be implemented. Any doubts up till here, students? Till here, any doubts? Any doubts, please ask. I can go back. Is it all fine? Okay. Please take down this table, okay, and come out with equations. So good, you have got equations for JA and KA. Anybody else? Is it correct what your friend is telling?
Yes, sir.
Okay, good. Then anybody got JB, KB? Yes, good. So you have got all the equations. So you can see here, okay, that we would finally get these equations. Okay, JA, KA, JB, KB, okay, JC, and KC. So these are going to be your final equations. So what do we do after we get an equation?
So logical gate implementation.
Correct. So we go with our implementation of logic gate. Good. So now here for this case, we know that we have to use our JK flip flop. So that is why we have taken this, and that is why we have taken the excitation of JK flip flop. Suppose say I tell you all to implement using D flip flop. Then what are the changes that you should do in this problem? Here in state diagram, would you make any changes? If I say implement using D flip flop, so in this state diagram, would you make any changes? Think. Yes, can I have some responses?
So would it be the same?
It would be the same. Why, Rohit?
Because the states are going from 0 to 1. The flip flop isn't, like, it's just state forwarding. So I don't think the flip flop change is affecting the state diagram.
Good. That's the absolute answer. So we do not have any influence of flip-flop here. Okay. So the influence of flip-flop is happening only when the implementation starts. Even here, you wouldn't have any changes. Even for this tabulation, you wouldn't have any changes. The changes would start from here. Okay. So if I tell you to implement using D flip-flop, then you will have to change this. Okay, so once the excitation table changes, then ultimately your responses or your circuit excitation table also does change. So which means all of these values also does change. All of these values also does change. So if these values are changing, then what is going to happen? The equations will also change, right? Okay. The equations also would change. Now, the final part is our circuit implementation, right? So let us take this JK flip-flop. Of course, we all used to always put the inputs towards the left-hand side. This time I thought, fine, let us go a little different. And I have put it at the bottom. Okay, fine. So you have your JA and KA, which is actually connected to DCX. Okay. So we will have two AND gates. One for B and the other one for C and X, okay, which multiplies C and X. So the output of this is going to be CX. Okay, here it's going to be CX. Okay, and here it's going to be B. So totally it's going to be B C X. So this will be the input for both JA and KA. So JA is done, KA is also done. Next, for JB, I have to make sure that I give for JB and KB CX, right? So I will take here as my input. Okay, so this thing will be given directly here from this point, right? So if I do that, then my JB and KB is also sorted out. Next, for JC and KC, only X I have to give as input. So only X is connected here. Okay, and these two branches out, and my JC and KC is also done. Now we have done only the J and K values. Okay, so ultimately now we know this is my A flip-flop. Okay, this is flip-flop A. Okay, flip-flop B and flip-flop C. Okay, so it will have its own outputs, true and complemented value, true and complemented, true and complemented. Okay. So the outputs, of course, you can mention anything as your output here, but here I am mentioning it as A bar, B bar, C bar, just like how you have Q and Q bar as your outputs, right? So here I am putting it as A bar, B bar, C bar, right? And these will be connected to each other. Okay, so which means we need to have a common clock also. Okay, so that is what is given here, and I am giving the clock here. Okay, which is common for A, B and C. So students, any doubts here as to how we have implemented this counter? Was it all clear? Is it a complex problem?
No, sir.
Okay.
No, sir.
So the only thing that you have to do here is you have to understand, okay, as to how to go about and use the values, how to use the flip-flop. So only then you will be able to do it. See, even though you know all these concepts, okay, even though you know how to get this done, just if your excitation table goes wrong, okay, simple, just your excitation goes wrong, then all these equations also would go wrong. If these equations goes wrong, then of course your circuit also will go wrong. Okay. So many of you during your exams, you will say, sir, I have attended the question and I should be getting full marks, or I should be getting a little bit higher marks. But that doesn't happen because somewhere you would have done some minute mistake. Okay, instead of CX, probably you would have written BCX. Okay, then instead of BCX, you would have written probably BC. Okay, so even if one of the inputs changes here, then your circuit, your total circuit also does change. If your circuit changes, then ultimately you wouldn't get your designed circuit. Fine. So is that all clear for you all, the concepts that we have discussed so far? Now take this as your assignment. Okay, what you can do is, as your homework, instead of implementing it in JK flip-flop, okay, try to implement using SR flip-flop. Try to implement the same using SR flip-flop. Okay, so you can probably copy down the question. Okay, copy down the question. So instead of JK, make it SR. Copy this example, and we will look into it in the upcoming class. We'll see if it's right. And once you start doing it, you will really get a feel of it as to how you are designing the counter and how you are implementing it. All your concepts will be cleared. If you just do this problem, okay, whatever concepts we have studied in a previous module will also be clarified. Okay. Yes, can I expect some responses? Will you all do it? Okay. Will you all do it for SR flip-flop? Okay. So will it be easy for all of you to get it implemented in SR flip-flop? What changes you have to do? What changes do you all have to incorporate? Yes, go ahead, Sayan. Yes, what changes are we going to do? We're going to change the excitation table, isn't it? And ultimately our combinations is going to change in the circuit excitation table as well, right? So fine, then we will end our lecture today, and we will catch up in the upcoming class.